I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life,
The podcast that helps you understand the chemistry of your everyday life.
This week, we're going to be talking about the chemistry of breathalyzers.
Okay, nice. The little things in the cars.
Yes.
I guess there's also
that cops have them.
Yeah.
That you blow into and they can tell if you're over the legal limit of alcohol or not.
Right.
And there are so many cool lessons in this.
Okay.
So we're going to start with what's called Beer's Law, ironically.
Okay.
For today's topic.
Is it like spelled the same way? Beer's Law?
Yes, but it's a guy named Beer.
That is very funny. Okay.
So Beer's Law is a way you can tell the concentration of something in a liquid based on its color.
Okay.
So say you have a little bit of a red dye, a red food coloring in some water. The more food coloring you have, the more red that water is going to get, right?
Right. I immediately thought of coffee. You can kind of tell if it's weak or strong.
Right.
It's not like exactly, but
yes,
you can a little bit.
Yes. So based on these colors, you can calculate the concentration of something in a solution.
Got it. Okay.
So you use what's called absorption spectroscopy to look at a color.
Mm-hmm.
And that's an objective look at a color based on wavelength. It's not based on a human's perception.
Right.
And they use this equation, this Beer's Law, to convert the color to the concentration.
Okay.
So usually you have to do a little work on the front end and make all these varying concentrations to get the right, curve of this much concentration equals this much color.
Yes.
So you have a standard. And then if you have another sample after that you don't know the concentration, you can just boom.
You know what this reminds me of is how I don't think you said the phrase Beer's Law back then, but this is kind of funny because we just talked about swimming pools last week.
Mm-hmm.
When I told you about how we used to test the water.
Yes.
And it would be different colors. We had to put it in this chamber.
Yes. Close the light.
Close the lid. Yeah. And then it would tell us how much chlorine or or the pH or how much flocculant, all these other things were in the pool.
Yes.
Was that using the same thing? Like,
I don't know about for the pH, but probably for the chlorine.
Okay.
If I had to guess.
Okay.
I've never been in a pool store though.
Yeah.
But at least something similar.
Interesting. And we just talked about pools. That's perfect.
Yeah, it's perfect. But that was when we talked about pools a long time ago, and I do not remember why.
Yeah, and I don't think the main topic of that episode was pools. I think it just somehow
came up.
Happened. Yeah.
Yeah. So I guess you guys have to go listen to all of our episodes. Bummer.
Yeah, it's a little Easter egg somewhere hidden on accident.
That's fun. Okay, so that's part of our episode today. And the other part of our episode today is oxidation.
Okay.
So we've talked about oxidation and reduction a lot. It's in rust. It's how batteries are powered. It happens.
Okay.
It's the movement of electrons. That's how we've always talked about it.
Oil rig.
Oxidation is losing. Reduction is gaining.
Nice.
Okay, so in organic chemistry, when we talk about oxidation and reduction, we take a slightly different approach.
Okay.
Because organic chemistry is the chemistry of carbon-containing molecules, and they typically go through oxidation by increasing the oxygen content in a molecule.
Okay.
Or decreasing the hydrogen content.
Okay.
That's the most common way we see it.
Okay.
So when I think of oxidation and reduction, I actually don't think of oil rig first. I think of adding bonds to an oxygen.
Oh, okay.
That's the organic chemistry version.
Got it.
And if, for example, we had alcohol, which is made up of an oxygen and a hydrogen, if you were to eliminate that hydrogen and add another bond to the oxygen, you could turn an alcohol into an aldehyde or a ketone, a different functional group, basically, that has more bonds to oxygen, less bonds to hydrogen, and that's oxidation to an organic chemist.
Okay.
And there's other things you use to achieve that oxidation. That's called the oxidizing agent. And those things are reduced in the process.
Okay.
So those are the two foundational lessons for what happens in a breathalyzer.
Okay.
So when you breathe into a breathalyzer, what happens is if there's alcohol in your breath, it will change the color of something in the breathalyzer, some chemicals,
Okay.
from a reddish orange to a greenish blue.
Interesting. And so when you drink, there's just alcohol just stays in your breath?
Yeah, that part is more biochemistry. So I didn't look into that as much as the function of the breathalyzer itself.
Okay.
But
It's like,
I think the alcohol in your breath correlates to the alcohol in your bloodstream.
okay. I was going to say, it makes sense. I mean, we all know it to be true because if you've drank or someone near you has, you can smell that on the breath for a little while.
Yes.
So it's not like that's a huge stretch to understand. But it is kind of strange now that I think about the chemistry of it, that those kind of molecules would just be in your breath for a while.
I'll probably have to do a different one to figure out how alcohol gets on your breath after it's been in your bloodstream.
Yeah. But breathalyzers do seem complicated enough for one.
Just one episode.
Yeah.
So you breathe alcohol out into the breathalyzer that has some chemicals in it. And if alcohol is present, at least some of those chemicals that are orange will turn to blue.
Okay.
So the thing that changes from orange to blue is called chromic acid.
Okay.
And it starts out as orange. It gets reduced. So the structure changes. It loses bonds to oxygen.
Mm-hmm.
And it turns blue.
Okay.
Now, the alcohol is what's being oxidized. It reacts with that chromic acid and it becomes, I think, ultimately another type of acid. It gets more bonds to oxygen. It gets oxidized and it doesn't change color at all. So it's kind of interesting because it's measuring the alcohol content based on the product of the reaction.
Okay, yeah. It's not really straight up looking at the alcohol itself.
Right. It's looking at alcohol goes in, A reacts with B to make C, and C is what we're measuring.
Got it.
So I think that's really interesting, personally.
Yeah.
And they use that spectroscopy to detect the amount of color change in the chromic acid and then use Beer's law to convert it to a concentration.
Mm-hmm.
So they know how much of the reduced substance there is and how much alcohol needed to make that.
Got it. Okay.
I think that's amazing.
That is crazy and also seems like it would take so long to figure out how to do. I don't know.
I don't know how they figured it out.
Wow.
Isn't it amazing?
Yes, seriously.
So I thought that was pretty cool. It's not a whole lot of information, but I feel like it's kind of a complicated situation, but also cool to imagine a color changing from orange to red when you just breathe in.
Yes.
To imagine a color changing from orange to blue just from breathing out alcohol on it.
Yeah, seriously. Yeah. That alone is already crazy.
I think you can look up videos online that will show you the color change of chromic acid before and after being reduced.
Interesting. Yeah, that's crazy. So, and also, can it just be done over and over? Because I know with breathalyzers that are installed in cars, they're just installed. Like they're just there. So,
well, I will say, I'm glad you brought this up because I wanted to say this at the beginning and I forgot that there are new breathalyzer technologies where they use other chemical methods to detect, such as, these are kind of big words, but mass spectrometry and infrared spectroscopy. I think they use stuff like that, but I don't know for sure.
Okay.
So, and I couldn't find any articles about it. So,
yeah,
it's hard to say, but I know they use these different kinds of detection methods. They don't only use this kind, but this is the original.
Got it. And the one that has the most detailed like chemistry about it that we are.
Yes, that I'm aware of.
I guess that makes sense because if some new company had a new version, they might not want there to be a public paper about how they did it immediately.
Yes. Yeah, and I think because there's less, it would just be, we put this in and chemically detect those gas particles. I think that's less interesting maybe to a high school class or something.
Right.
So,
yeah.
And also, I have some other adaptations of the breathalyzer that are being worked on that I'll share with you after you teach it back to me.
Okay.
Those are your fun facts for this week.
Okay, sweet. This is going to be a little tough for me, I think, but.
Yes, it is a little tough, and I couldn't think of a good analogy.
Yeah.
other than the food coloring situation.
Right.
But it's not just getting more and more concentrated, it's also changing colors. That
Yes.
kind of makes it hard.
Yeah, there's so many different aspects of it. It's almost like you need several analogies rather than just one that would work for all of these things.
Yes.
It was like it'd be a little bit too shoehorned in to get one thing to work. But okay, so first you drink some alcohol.
Yes.
And for totally other more complicated reasons, alcohol stays in your breath.
Yes.
So when a person then breathes into a breathalyzer, there's those molecules of alcohol.
It's called ethanol, the one that's usually
right.
drinking alcohol.
Right. We talked about the different kinds of alcohol before. Yes. Okay. Ethanol.
But this would work with any kind of alcohol in your breath. So if you just dropped some drops of isopropyl alcohol, hand sanitizer, whatever, it would still oxidize.
Oh, okay.
Yeah. But specifically when you're drinking, it's ethanol.
So it's ethanol, and molecules of it go into the breathalyzer. And when they arrive, they meet the chromic acid.
Yes. And I think it sort of bubbles through. I think your breath goes through this liquid for the classic breathalyzer.
Got it. Okay. And then this is where I'm going to struggle because of the whole oxidation thing being hard to wrap my head around. But so the ethanol then reacts with the chromic acid, right?
Yes.
And in that situation, sounds like it's kind of complicated, but that on the one hand, a new thing is kind of created.
Yes.
That more directly reacts with the chromic acid. But the overall thing is that the chromic acid loses an oxygen.
Yes.
And the ethanol gains one.
Yes. So, I'm not sure the new thing reacts with the chromic acid. It's responsible for the color change of the chromic acid.
Okay.
So what you said is right. The alcohol gains more oxygen, meaning it's oxidized. The chromic acid loses oxygen, meaning it's reduced. And that reduced state is the new color.
Got it.
Okay.
And then what'd you call the thing that can look at the color of stuff?
Oh, it's called absorption spectroscopy.
Absorption spectroscopy. After that's happened, it has already been ready to go, and it's just kind of waiting for that reaction to happen and the things to change. And then it's like, boom, I'm looking. I know what concentration of colors to look for and stuff.
Yes.
And I'm in a dark, controlled situation where I can shine a light, and then it tells us how much. Because that whole reaction, working backwards, sort of, how much alcohol it thinks was present.
Yes.
To do that.
Yes. So the absorption spectra is usually what they say for what it produces, gives you the key that you need to plug the numbers into Beer's law and calculate how much of a concentration of the reduced products there are that's blue. And you can basically work backwards from there to figure out how much alcohol caused that.
Okay.
So it's kind of a more complicated process because it has so much chemistry. So you're getting an oxidation reaction, you're learning about absorption spectroscopy, and you're learning about Beer's law all in one thing.
Yeah. Yeah, dang.
And it's kind of a new way to think about oxidation. You can still think about the electrons moving around if you want to, but I like this way of thinking about it. I imagine if alcohol gets oxidized, in my mind, I'm not counting up electrons. I'm looking to see where new oxygen bonds have formed. Right.
And that's, I think one time you described, it's kind of confusing that it's even named oxidation.
Yes.
Is because of that. Is because in its earliest, the people who were kind of observing that first were seeing that changed.
Yeah, I think that's true.
Because it does sound strange for it to be like, oh yeah, that word means the changing of electrons. It's like, well, why does it have basically the word oxygen in it then?
Yes.
If it's possible for it to happen without oxygen.
Yeah. Well, and I think for rust too, the oxidizing agent is oxygen, I think. So sometimes I get oxidizing and reduced mixed up in terms of which one's doing what, but oxygen is reacting when rust is forming. And so I think that's also part of it too. So oxygen has a lot to do with oxidation because oxygen brings a lot of electrons along with it.
Right. Okay.
So.
Gotcha.
I think that was a good overview. The biggest thing to me to focus on that I think is cool is the alcohol in your breath is causing a reaction, which causes chromic acid solutions to turn from this orange-red color to its reversed version. It has an ion present, which is why it's green. So it changes colors, and then we can look at that color with a computer and an instrument and tell us how much alcohol did you breathe in.
Yeah.
And that's amazing to me.
Dang.
Yeah.
That's cool.
So cool.
Man, I wonder how long it took for people to put that together. Like, probably somebody out there knew, a lot more about the color changing stuff and all that stuff. And then somebody else probably was like, man, if only there was a way we could detect how much alcohol was in somebody's breath.
Yeah.
Like, I just wonder how long it took to put those puzzle pieces together.
I don't know, but some cool things that they're doing with breathalyzers now, and they're using totally different technology than the chromic acid. But similarly, people with diabetes tend to have a higher level of acetone in their breath. And so they're trying to develop a breathalyzer that can detect for acetone similarly to how these breathalyzers detect for alcohol to determine the glucose level or how people are doing with diabetes.
Okay.
Isn't that cool?
Yeah. Wow.
They also are working on developing a breathalyzer, and they use like nanoparticles to recognize organic compounds and machine learning to teach computers to recognize COVID-19.
Whoa.
I know.
That's crazy.
Isn't chemistry amazing?
Yes, seriously.
So there's all kinds of applications to what chemistry is in our breath and how that manifests in our bodies.
Seriously. Wow.
So good job, chemists, for figuring this out.
Yes. It's one of those very futuristic things too to think about. Like as a layperson thinking like, oh, I'll breathe into this and it detects this seems so much like one of those like, oh yeah, that'll be in the future someday, but maybe like way beyond our years. But it's like, no, a lot of it is already happening.
They're working on it right now.
And it's not like, I mean, the chemistry is very impressive, but it also is not like insane. It's not completely understandable. I don't know. You know what I mean?
Yeah. It's totally within your grasp. This is one of my favorite examples for how oxidation works in the real world and for an application of chemistry in everyday life. I absolutely love it. So I'm glad we got a chance to talk about it today.
Me too. Very interesting.
Speaking of things you're glad about, got anything that makes you happy from this week?
Well, nothing huge, nothing like mind-blowingly awesome like some weeks. Most of mine are mind-blowing, I would say, most weeks.
You're like, I got the new coffee. This is mind-blowing.
Yeah, that's right. So this, oh yeah, did I talk about that in one of them?
I think you did talk about new coffee in one of them.
Cool. Yeah, exactly. That's, all really cool stuff coming out of the Robinson house over here. But this past week, the biggest thing was really just improving our Wi-Fi, which in this day and age is a huge deal, at least for most of us, even maybe it shouldn't be, but we live down on a double cul-de-sac kind of deal, and the cell signal is very bad down here. So that's not great. And that means that the Wi-Fi's got to be good because we do have control over that.
And everyone's using it.
Everyone's using it. And, lots of, obviously, most of messaging apps and stuff like that have a Wi-Fi version or using Wi-Fi, like if you would use iMessage, for instance, and stuff. So whenever we have people here or even just ourselves, it's like we're more dependent on Wi-Fi than we have been on in other houses we've lived in.
Yeah.
And somehow the signal hasn't been very good in our house. So I put it off for a long time, but eventually finally just got a mesh Wi-Fi system, which, nerds know how cool that is. But basically the gist of it is just that it covers our house much better in in Wi-Fi.
Cool. I've never heard of that before.
Okay, here's the lay people's version of how it works.
Okay, teach me. It's my turn to learn.
So traditionally you have one router.
Yes.
And even in the old days when you have like extenders or whatever that you'd plug into that outlet and have an antenna or whatever, those just kind of perpetuate the signal further, but they don't really, they're not very strong. That makes sense.
They're not generating a new signal. They're just lengthening your current signal.
Correct. And so you might be like, oh, sweet, I'm getting Wi-Fi way out on this far end of my house now, but its speed might be horrible. You know? It just makes it larger in area, not necessarily, fast everywhere.
Right.
So what mesh Wi-Fi does is with each, you have multiple routers, and they're not extenders as in the old school way.
Right.
And what they do is they make a super strong connection to each other.
Wow.
Kind of like Bluetooth. So my understanding is that it's like before you even run internet to them, they just know where each other are, kind of thing. Have some version of a signal, kind of like Bluetooth, that's local to each other.
Yeah.
And it's like, sweet, we're very connected. Like, let's get a super strong brain connection between each other.
Okay.
And then when you hook Wi-Fi up to like the internet kind of input to the main router, it runs through the connection to the other routers as well.
Wow.
So it's almost like you've created an invisible pipe between these other ones.
Yeah.
And then when you run water through it, it connects way better.
Yeah.
And
so there's Wi-Fi all over your house.
All over our house, including like in our backyard, which we hang out back there and have people come over and hang out back there.
I took an exam out there once.
Yep. And if you need Wi-Fi out there because there's no cell coverage, then you
have it.
You have it now. So
that is very cool.
Yeah. So it's kind of a big improvement over here.
It makes everyday life better, but it's not a huge deal.
Yes. Yep.
Mine is actually kind of similar.
Okay.
So I moved into an apartment with my husband after we got married. Typical. And we went through everything and got rid of our college stuff. We donated to other college students, our like bachelor pad situations.
Yeah. Yeah.
And we got some stuff off our wedding registry and have our whole kitchen set up now. And I was just noticing that we have a lot of pans in this one cabinet. And I've been really working on minimalism. I'm like, why do we have all these pans? I thought that we were trying to streamline our pan system, which we did, but we're also in a small apartment.
Yeah.
So we still have less pans than a lot of people, but more pans than I want in our apartment.
Got it.
So I convinced my husband to let me put a small Teflon pan that we have in storage. Because I use the cast iron pan that's that same size all the time. So what's the point of the Teflon one?
And he was kind of attached to the Teflon one.
He was kind of, and Teflon's kind of evil, so like why?
Yeah.
So got that one in storage, plus a big stock pot, which we rarely use because it's not even soup time. It's not soup season.
Right.
And a large saucepan. I think it's called a sauce or saute. It has walls, but not as high as like a pasta pot.
Got it. Yeah.
That we will probably use a lot, especially as we have more people in our family. But right now, cooking for just two people, you just don't need it.
Got it.
So we've moved all these pans into storage. And now our pots and pans cabinet is so much more functional.
Nice.
I'm just happier every time I go in there.
Very cool. Dude,
so
that's awesome.
Similar to the Wi-Fi.
Yeah.
Where it doesn't seem like a big deal, but it makes every day less annoying.
Yep. 100%.
It's the best.
I love that. That is great. And kudos to you guys for being able to relinquish that one Teflon pan. You know?
I mean, we still have it.
Right. For
Hopefully
now.
not for long.
Yeah. I was gonna say.
plotting to get rid of it.
Yeah.
Yeah, it is. I will say that's a nice thing about, we've been learning more about minimalism and not being so attached to your things and noticing the burden that things put on you, even though they seem like they're going to help you. Sometimes they just can be more of a burden.
Right.
And so I've streamlined my wardrobe and I've streamlined the pots and pans cabinet and, just having less stuff really does make things easier.
Yeah.
So I really loved it. If you are a maximalist, more power to you, but having less things has made my life easier. It's less things to clean. You know, it just is a lot simpler.
Yes.
So
I hear that, dude.
It makes me happier every time.
Yeah.
All right, Jam. Well, thanks for convincing me that minimalism is cool and making me watch that documentary. And thanks for coming and learning about the cool nature of breathalyzers. Thanks to all of you listeners as well. We could not do this without you. It's so fun that I get to share what I'm excited about in chemistry with all of you every week.
And we're glad that you want to, because we're thankful, and thanks for teaching us and breaking down these very complicated chemistry lessons from our everyday life into ways that at least me as a layperson can understand.
You are so welcome. I think it's really fun.
It is really fun. And if you have any fun ideas, things you wonder about that might be chemistry, please reach out to us on Gmail, Instagram, Twitter, or Facebook at Chem for Your Life. That's Chem, F-O-R, Your Life, to share your thoughts and ideas with us. If you'd like to help us keep our show going and contribute to cover the costs of making it, go to ko-fi.com/Chem for Your Life to donate the cost of a cup of coffee. But if you're not able to donate, you can still help us by subscribing on your favorite podcast app and rating and writing a review on Apple Podcasts. That also helps us to share chemistry with even more people.
This episode of Chemistry for Your Life was created by Melissa Collini and J.M. Robinson. References for this episode can be found in our show notes or on our website. J.M. Robinson is our producer, and we'd like to give a special thanks to A. Kiosong and In Newell, who reviewed this episode.